You are wrong. Well, maybe.
If you are watching this video and clicked on it not by accident, then you're probably interested in space, which means you may have some understanding of one of the most important parameters in astrophysics, or in just physics, the speed of light. Someone knows its approximate value, 300,000 kilometers per second, or about 186,000 miles per second, and some may even recall the exact value, which is 299,792,458 meters per second. Someone will immediately recall that the speed of light in a vacuum is unique because it is always constant regardless of the chosen reference frame.
But at the same time, it's quite possible that some of you may have one or maybe even several misconceptions or not entirely accurate ideas about light and its speed. In this video, I decided to gather several such misconceptions.
Today, let's talk about whether it is possible to stop light, and why does it even slow down in the first place? Is the speed of light really about light? Is it true that we cannot actually measure the speed of light? And why don't we see images of galaxies distorted, given that light takes different amounts of time to reach us from the far and near edges of galaxies?
My name is Andrei, and this is Cosmos Elementary.
The speed of light is an absolute unbreakable barrier of speed, the maximum speed in the universe.
But the speed of light is not just the speed of light. Well, of course, I mean the speed of light is the speed of light, but not only of that. The familiar term the speed of light may be a bit misleading. One might think that this is the property unique to light. However, that is not the case.
In the context of interstellar travel, the possibility of moving through the universe at the speed of light is often discussed. However, as we well know, this is impossible. And let me briefly remind you why is that so. There are two most popular explanations. One is related to time and, let's say, freezing of time. And the other is related to mass. It suggests that, according to special theory of relativity, the faster an object moves, the greater its mass becomes. When the speed of an object relative to an observer approaches the speed of light, its mass begins to approach infinity. And to continue accelerating, it would require an infinite amount of energy.
Hence, we can conclude that no object with non-zero mass can reach the speed of light in a vacuum. Well, as many of you probably know, this caveat about the mass is very important. To be able to move at the speed of light, an object must have no mass, and photons are massless particles.
And light, and not only visible light, but any form of electromagnetic radiation in a vacuum, travels at the speed of light. But photons are not the only massless things. Let's take a look at the standard model of elementary particles. Here we have a photon, and its mass is 0. But next to the photon, there's also the gluon, and as we can see, its mass is also 0. And this version of the table also adds graviton, which is so far only a hypothetical particle. It could be the carrier of gravitational interaction or the quantum of gravity. We haven't detected it yet, and it's uncertain whether we can ever detect it. However, according to the theoretical predictions, the graviton should also be a massless particle. Some of you have probably heard that gravity propagates at the speed of light. This idea is not new, but until relatively recently, there was no reliable way to directly test it. However, when events of gravitational waves started to be detected, it became possible to verify this. Electromagnetic radiation and gravitational waves from the same event were recorded basically without delay. So it seems that gravity does indeed propagate at the speed of light. So yes, if for some reason the sun were to suddenly disappear, we would still see its light for another 8 minutes, but also Earth would continue moving in its orbit for the same 8 minutes, and only after that it would embark on a journey through the galaxy. There are also particles with very small mass, but they're not massless, such as neutrinos. They move at the speed close to the speed of light. However, some models allow for the existence of certain types of neutrinos that could be massless. Sometimes it might seem like neutrinos even surpass light speed. For example, the first stream of neutrinos from the supernova SN 1987A reached Earth almost 8 hours before the visible light. However, it's not that neutrinos somehow managed to overcome the speed of light barrier. The thing is that the collapse of a star is not instantaneous. Neutrinos, which weakly interact with matter, were able to leave the stellar interior and start their journey through the universe before the shockwave reached the surface of the star, and the flash of light happened. Cosmologist Carroll, in an interview with Think Inc., said that the reason why the speed of light became known as the speed of light is just historical and is simply because it was measured earlier.
But in general, this maximum speed is more like the speed of causality, the maximum speed at which one object in the universe can affect the other. There was a video about this on PBS Space and I leave a link to it in the description. Yes, light in a vacuum does propagate at this speed, but it's not just about light. But I keep saying speed of light in a vacuum. Again, many of you probably know why I'm making this clarification.
Almost 300 million meters per second is the speed of light when it propagates through a vacuum, where there is no matter. However, when light passes through a medium where there is some matter, whether it is gas, liquid, or something solid but transparent like glass, it appears to slow down. And this is related to another common misconception that I even came across in some popular science articles while writing the script for this video. Very often, the explanation of why light slows down is not really correct.
So here is the light source, and here is glass. Light outside the glass propagates at the speed of light. Let's ignore air for now, it actually does have an influence, but for now let's imagine that there is vacuum around glass. So here, before it enters the glass, light propagates at around 300,000 kilometers per second. But inside the glass, it slows down. One might think that it slows down insignificantly, but in reality, it travels inside the glass about 1.5 times slower, so about 200,000 kilometers per second. How do I know this? Because of a parameter known as the refractive index.
Here's a simple table with values for different substances. For glass it is 1.5, meaning light moves in glass about 1.5 times slower. For water it is 1.33, and for diamonds it is almost 2.5.
But why does this slowing down happen? Intuitively, one might think that it's like when I'm first walking on the shore and then enter the water. So when I walk through the water, it takes more effort and I move more slowly.
Moreover, it doesn't explain another interesting fact. Light travels at normal speed here, then slows down here, but when it leaves the glass, it speeds up again. Where did it get the energy from in that case? From nowhere. It's just a bad analogy.
Very often, two explanations are used here. I came across both of them multiple times and, well, both of them are incorrect.
According to the first explanation, when a photon of light enters a medium, in this case glass, it begins to interact with particles that make up the glass, sort of bouncing off them. It constantly changes its trajectory. Along all these trajectories, it moves at the same maximum speed of light. But the distance that an individual photon covers through the glass is longer. So at the same speed, it just takes more time for it to travel from here to here. But, as I've already mentioned, this explanation is incorrect, because it doesn't align with what we observe. If I point the beam at the right angle, it exits on the other side in the same direction. If we change the angle, the direction changes, but this happens predictably. But light can scatter in different directions. If it first bounces off of one atom and then off of another, can we be sure that it will return exactly on the same path it entered the glass? Certainly not, especially when we are talking about not just one photon, but a huge number of them. In short, if it worked like that, we wouldn't see such a predictable beam emerging on the other side. This explanation is repeated in various articles and even on large channels like in this video on minute physics. In the second explanation, it is said that photons of light, upon entering a medium, once again interact with atoms Specifically, they are absorbed by the atoms, and then the atoms re-emit them. And this process takes time and causes a delay.
There are several problems here. Atoms can indeed absorb photons, but firstly, certain energies of photons are needed for specific atoms, so it doesn't work in a way that any atom can absorb any photon. And secondly, here arises the similar problem to the first explanation. The re-emitted photon cannot remember the direction in which it was moving prior to the absorption, so it will be re-emitted in a random direction. Consequently, we wouldn't see a beam in a specific direction. Rather, the light would scatter in all directions.
In reality, things work differently, and there are several more accurate explanations. For instance, when considering light in this context, it is more appropriate to think of it not as particles, but as waves. Glass consists of atoms, and atoms contain electrons, charged particles. Light waves are disturbances in the electromagnetic field.
They influence the electrons and make them oscillate. The oscillating electrons in turn start producing electromagnetic waves or radiation themselves. So the light that propagates through glass is the sum of original light waves and light waves generated by electrons. The observed slowing down is related to this combined wave. Also here, phase and group velocities are important.
So this is a simple wave, and in this animation a more complex wave is depicted. It is composed of different waves. Here it is shown how one wave at the bottom is formed by the combination of three waves. The red square represents the phase velocity, which is the speed at which the peak of a wave moves. The green circles represent the group velocity, showing how quickly repeating patterns move between the green circles, essentially the pulses of light. So, when light interacts with waves from electrons, it is the group velocity that slows down.
This explanation is not very intuitive. Also, I simplified it and didn't delve into detail about phase velocities and stuff like that. But at least it is more accurate than previous two explanations. There are actually other explanations that involve quantum effects and probabilities, and also the thing called Polariton.
This is a quasi-particle or a complex combination of photons and their interactions with matter and its vibrations. This quasi-particle possesses mass, and hence it has to slow down.
If ordinary glass can slow down light by 50%, understanding how it works allows scientists to manipulate this process and slow it down much more significantly. In fact, researchers have done this in lab experiments, slowing down light by hundreds of times, and even kind of stopping it for a brief period.
And it's not just visually stopped, as in videos where people synchronize the camera shutter with light pulses in a certain way, creating an illusion that light has stopped, as shown for example in this video by Tom Scott. Instead, it actually freezes. By manipulating matter, influencing it with lasers, they created unique traps for light. And there are even images of this. Here they are. In theory, this could be used for storing information. By the way, an interesting conclusion can be drawn from all this. Theoretically, there is no absolute emptiness in the universe. Even in the emptiest regions, there is still gas, photons from cosmic microwave background radiation are everywhere, and light interacts with something one way or another. So even in the emptiest regions, light may move, albeit very, very insignificantly slower than its maximum speed.
It's time to talk about the elephant in the room, the big issue.
I've mentioned before that we know the speed of light in a vacuum with high precision, 299,792,458 meters per second. But the problem is that we don't actually know the speed of light.
What am I rambling about? Well, here we need to clarify that we actually don't know the one-way speed of light. For physicists or for those who are interested in this topic, it's not a big secret, but people started to talk more about it a few years ago.
When Veritasium released a video titled "Why No One Has Measured the Speed of Light."
Is that true? Well, in short, yes. Veritasium video covers this in detail, but I cannot ignore this aspect completely. So what's the issue?
The special theory of relativity is one of the most successful theories in history, confirmed by numerous high-precision experiments. At the core of this theory is the invariance of the speed of light regardless of the reference frame.
All those examples about, like, if I'm driving a car at 50 kilometers per second and then I throw a ball out of the window from the car in the direction of the motion at 20 kilometers per second, then the ball speed will be the sum of the speed of the car and the speed of the ball itself, so that is 70 kilometers per second. But again, with light it doesn't work that way, and if a photon is emitted from a moving object, the speed of the object is not added to the speed of the photon. It's always around 300,000 kilometers per second.
However, before Einstein, it was not considered necessary for it to be so. In the 19th century, there was an idea that since light is a wave, it must require a physical medium for propagation, like water for ocean waves or air for sound. This hypothetical medium was called the ether. So if Earth is moving through this medium, Earth's motion should affect the speed of light.
It sounds like a theoretical prediction that one can attempt to verify.
That's exactly what Albert Michelson and Edward Morley did in 1887. They set up an experiment on a rotating platform with a light source and a semi-transparent mirror at a 45-degree angle. This mirror reflected the part of light to one mirror and allowed part of light to pass through to another mirror. Both mirrors were at the same distance from the center, and the light from these mirrors was supposed to reach a detector. If propagation of light depended on the Earth's motion through this ether, then with different orientations of the platform in relation to the motion, we would observe different patterns on the detector, and that would have proven the existence of ether. But the experiment showed exactly the opposite. Regardless of the direction, experimenters observed no variations in the speed of light. Later on, the special theory of relativity emerged, in which neither space nor time was absolute. Rather, the speed of light was absolute. And this leads to the well-known, albeit strange, effects such as time dilation and length contraction for moving objects relative to an observer. All of this, together, lies at the heart of the issue of measuring the speed of light.
So how can we measure the speed of something? It seems straightforward. If we have an object that covers, let's say, 100 meters, we know the distance. Now we just need to measure the time it takes to cover that distance, and we will know the speed. And the speed of light we can measure is generally determined in a similar way, yet with one small but significant caveat. So we have a light source, and we send light into a mirror. Yes, a very beautiful mirror. So the light reflects back, returns, and is detected by a detector. And the timer tells us how much time has passed between the emission of light and its return. And if we know the distance, we can calculate the speed. So we successfully measured the two-way speed of light, the time it took light to travel to the mirror and come back to the detector. And no matter what we do, whatever the experimental setup we have, whatever the conditions there are, the speed of light in a vacuum measured this way is always the same, 300,000 kilometers per second. But what if in such round-trip experiments the light travels this way faster, but then on its way back it goes slower, or even much faster this way and then instantly comes back after the reflection? So in all those cases, the overall travel time would be the same, and also average speed would be the same. And that's what we actually measure. Average speed. It might seem simple. Instead of a mirror, just place a second detector with a timer on the other side. Measure the time not for the journey from A to B and then from B to A, but only for the journey from A to B. But that's apparently impossible. For accurate measurements, both timers at both points have to be synchronized. If our timers are already separated before we send the signal, we need to synchronize them. If we send the signal from one timer to another for synchronization, it will travel at maximum speed of light, but still it will arrive with a delay. During synchronization, we need to account for this delay. But this delay is precisely the thing that we are trying to measure, the speed of light in one direction, and we don't know it yet. If we initially keep two timers together, synchronize them, and then move the second timer to a different point, then while it is moving, it is subject to the effects of special relativity, and specifically the effects of time dilation. By the time it reaches the desired point, it will be out of sync.
Certainly, this doesn't stop scientists from attempting to devise a method to measure the one-way speed of light, and not just scientists.
One might think, what if we synchronize two timers from a point in the center between them, like this?
Or to send them at the same speed but at different times, or to spread them very slowly, or to launch light in a closed loop.
In practice, all of the methods suffer from similar problems, but we still measure the same constant speed of light. The effects of special relativity still interfere, even when you think that you are measuring the speed of light in one direction.
Upon closer examination, it turns out that it is two-way, as was the case with this experiment, which was later refuted.
What if light is anisotropic and everything in the universe depends on the direction?
If that's the case, it seems like the universe should look different. If there's one particular preferred direction when looking deep into space, the universe would exhibit differences. Considering the finite speed of light in one direction, we could see galaxies that are younger than those in another direction. This would also be reflected in the cosmic microwave background radiation. We don't observe this. The universe appears to be the same in all directions on large scales. So, there is no preferred direction for light? However, it's not necessarily the case. There was a study where scientists argued that even if there is a preferred direction, the effects of special theory of relativity, such as time dilation and length contraction, would compensate for it, and we would still observe the universe to be the same in all directions.
You might even come up with your own idea of the experiment which you may think will measure the one-way speed of light. And here I'll remind you that scientists have been grappling with this issue for over 100 years. If this idea came to you in a couple of minutes while watching a YouTube video, chances are specialists have already considered it. And since no one has measured the speed of light in one direction, in theory we cannot confidently say that it doesn't differ in different directions. And also it means that those methods have not succeeded yet. On the other hand, who knows? Maybe your idea would actually work. In that case, it's worth writing an article for a scientific journal. Maybe you will make a breakthrough in physics. So why do we usually talk about the speed of light without this caveat about one-way speed?
In general, we assume that it is the same in both directions, primarily because Einstein stated so. More precisely, he wrote about this in his famous paper in 1905, where he discussed this problem among other things.
In a sense, it's just an assumption. But interestingly, even though we don't know it for sure, and it's not certain we will ever know it,
special theory of relativity still works, and we use it in applications such as GPS and other technologies. Even with the two-way speed of light, we measure the distance to the moon and planets, launch spacecraft to them, and actually reach those planets and don't miss. As I mentioned earlier, there is a vast number of experiments confirming the special theory of relativity.
I have one more interesting question that I've heard many times. Why don't galaxies get distorted?
So we'll know that the speed of light is finite and it takes time for light to reach our eyes, telescopes or cameras. When we look at the night sky, and actually at anything, we see not the present moment but the past. We receive photons that were emitted some time ago, and the farther the object, the further into the past we look. Looking at a constellation or an asterism like the Big Dipper, we simultaneously see different moments in time. For instance, this star is roughly 40 light-years farther away than this star. Therefore, we see one of them as it was 40 years earlier than the other. But constellations are not real structures in the sense that they are only patterns formed by stars as observed from Earth. Galaxies, on the other hand. The question goes as follows. Galaxies are large. In diameter, they can span tens or even hundreds of thousands of light years. If we observe a galaxy at some angle, then the light from the stars located at its far edge takes more time to reach us than the light from the stars at its near edge. Why then do we see beautiful spiral galaxies? and their appearance is not distorted when they are rotating, similar to how my face distorts when using this filter. Or is it possible that we actually see them distorted, but in reality they look different?
Well, in short, the image does get distorted, just not to an extent that it becomes noticeable. One can delve into calculations, but I'll describe the situation in general.
If we see a galaxy face-on, we are observing it, let's say, from above or below, and all of its regions are roughly at the same distance from us. Then there is no problem. But if it is at an angle, then this effect comes into play. If we use our own galaxy as an example, the diameter of our galaxy is approximately 100,000 light years. So if we observe such a galaxy from the side, and it is facing us edge on, then the light from the stars at the far edge reaches us 100,000 years later. However, when observing from the edge, we won't get a clear view of these stars due to galactic dust.
To see the spiral structure, we need to view it not edge on, but at some angle. Then the stars on the far side will be closer than 100,000 light years. However, even if we take it as a maximum value, we still need to account for galaxy's rotational speed.
The linear velocity of stars, regardless of the distance from the center of the galaxy, is approximately the same. And for Milky Way, it is about 200–250 kilometers per second. Our Sun completes a full orbit around the center of the galaxy in over 200 million years. So 100,000 is only 0.05% of 200 million. So the delay exists, but it is very insignificant, as are the distortions. To significantly distort the beautiful spiral structure of a galaxy that we observe at an angle, it would require a much more substantial delay and distortion, but it is not the case. Therefore, we see such galaxies almost as they truly are, with only minor, barely noticeable distortions.
In this video I touched on several interesting topics, however, of course it is far from covering everything. I'm sure you've come across some other misconceptions or inaccuracies related to the speed of light, so write them down in the comments. Thanks for watching. Links to all of the sources are as usual down below in the description. If you enjoyed the video, leave a like, comment, and of course subscribe for more videos in the future. And if you really enjoyed it, feel free to share this video with your friends, family, and everybody else. Okay, bye.